Welcome everyone to week 4, part A. This week we're diving into SQL, Postgres, the language that powers every healthcare database you'll ever work with. This is the first of 4 parts. This week covering SQL and health information standards. Part A focuses on the data definition language, DDL, the commands that define your database structure. Part B will cover the querying data with the select statement, and by the end of the day you'll be able to create, modify, and safely remove database tables. So let's see what our 6 main objectives for today are in review. And we've got a lot to cover. This is pretty heavy stuff, but you'll get exposed to it over and over again and you'll become very comfortable with it, so don't get overwhelmed. But first, we want you to understand the historical context. Why Postgres became the go-to choice for healthcare. Second, we'll talk about the categories of commands, the DDL, DML, and DQL, the data definition language, data manipulation language, and the data query language statements. You need to know which tool to use and when. And third, we'll talk about data types, choosing the right container for your healthcare data. And this matters more than you think. Fourth, we have create table for building tables with the proper constraints from Jump Street, from the very beginning. That's so important. And fifth, we'll have an alter table, evolving your schema as requirements change, laws change, and you need to be able to update the format of your table. And sixth, the drop table, the scary thing, the nuclear option, when and how to use it safely. Healthcare databases require extra care due to laws, regulatory requirements, and patient safety implications. So you might wonder why we're using Postgres and not like MySQL or SQL Server or one of Oracle's versions. And there are good reasons, very good reasons. Open source. That means you don't have to pay a licensing fee. It's a very transparent code base. This leaves you resources for other things that you might want to do, like improving your code or your project. The transparent code base means security researchers can audit it. ACID compliance is non-negotiable in healthcare. It's a requirement. So it's essential that you're ACID compliant. So if a medication order is entered, it must be recorded completely or not at all. No partial transactions. Extensibility is also important. We have native JSON binary support for FHIR resources, which we'll talk about later. And you've got the universal UUID support for patient identifiers, like for PostGIS, for graphic information systems, for geographic health analysis. Enterprise-grade reliability means major health systems like Kaiser and the VA, they use Postgres. It's also HIPAA compatible, which means it supports encryption at rest and while data is in transit. So you have comprehensive audit logging and granular role-based access control. These are important. And another clarification, Postgres itself is not HIPAA certified. No database is. But HIPAA compliance comes from how you implement and configure it. Postgres gives you all the tools. You provide the policies and procedures. Let's give you a quick history lesson. This context will help you understand Postgres' philosophy. In 1986, it started as Postgres at the University of California, Berkeley, under Michael Stonebraker, who was a Turing Award winner, which is a big deal. It's like the Nobel Prize in computing. The name means post-ingress. Ingress was a big database at the time. It was a big database project. In 1996, it was renamed Postgres, or PostgreSQL, when SQL support was added. The community debated the name for years. Through the 2000s, enterprise adoption grew as companies realized open source didn't mean it was for dummies or amateurs. In 2017, PostgreSQL 10 introduced native partitioning, critical for large healthcare datasets with billions of rows. PostgreSQL in 16 in 2020, introduced in 2024, is the current stable release with improved performance and security features. Why this matters? 35 years of continuous development means battle-tested reliability. Healthcare can't afford database crashes. SQL commands fall into 5 categories, and today we're going to focus first on DDL. DDL, Data Definition Language. It includes create, alter, drop, and truncate. These define the structure, kind of the skeleton of your database. And this is today's focus. Data manipulation language, on the other hand, includes insert, update, and delete. These manipulate the data within the tables. And we'll touch on this, especially as we go into future weeks. And the other, data query language, that includes the select statement that retrieves data. And in part B of this lecture, we'll focus on that. And DCL, the data control language, involves grant and revoke. It controls who can do what and is critical for HIPAA, minimum necessary access. TCL, the transaction control language, includes commit, rollback, and save point. It manages transaction boundaries and ensures ACID compliance. So think of it like building a hospital. The DDL builds the rooms. DML fills them with equipment. DQL finds what you need. DCL controls who has the keys. And TCL ensures construction phases complete properly. Understanding this distinction prevents costly mistakes. The purposes. Data definition language defines the structure, the blueprint, while data manipulation language manipulates the data, the contents. The commands, DDL uses create, alter, and drop. DML uses insert, update, and delete. Auto commit is critical. Data definition language changes commit immediately. You cannot roll back a drop table. And we'll go over this many times. Data manipulation language can be rolled back until you execute a commit command. So what it affects, data definition language affects tables, indexes, schemas, and views. DML, data manipulation language, affects rows within tables. How about a healthcare example? Data definition language would be create a patient's table, while data manipulation language would be add John Smith as a new patient. But here's a real world warning. I've seen junior database administrators, DBAs, accidentally drop a production table thinking they could undo it. You can't. Always test DDL in developmental phase first so you can undo and not create any irreparable mistakes. So what types of data matter in healthcare? Choosing the right data type isn't just academic, it has significant consequences. Firstly, storage efficiency. An integer takes 4 bytes of physical space. A big int uses 8. Well, if you're keeping millions or billions of values, that can make a big difference. So you can make a difference of terabytes in the size of your files. Now, data validation is built in. If you define age as a small int, Postgres won't let someone enter 25 in text with quotes or minus 500. The database enforces rules. Query performance improves because comparing integers is far faster than comparing strings. Index date columns enable efficient range queries. For compliance, auditors ask, how do you ensure data integrity? Proper data types are part of your answer. For interoperability, FHIR resources expect specific formats. Health Level 7 HL7 messages have defined data types. Your database should align with them. So you have to learn the HL7 and FHIR data structures to be able to be compatible with your local application. And data types are like medication containers. You wouldn't store liquid in a pill bottle or pills in an IV bag. You have to match the container to the contents. Numbers are everywhere in healthcare. IDs, vital signs, account numbers. So integer is your workhorse, ranging from -2 billion to +2 billion. Used for the patient ID and counter ID. Most counters. Small integer has a smaller range, -32K to +32K, but uses only 2 bytes. So this is perfect for things like heart rate, which usually runs like between 40 and 200, or age, which is usually between 0 and 150, and blood pressure readings. Those will fill nicely in a small integer field. You can use big integer when integer isn't enough. Large health systems might have claim IDs that exceed 2 billion over decades. Decimal with precision and scale provides exact precision. We always use this for money. Like decimal 10,2 means up to 99,999,999 cents. Never use float for money. Floating point has rounding errors. Serial is auto-incrementing integers where Postgres manages the sequence for you. This is perfect for surrogate primary keys when you need a sequence number. Let's think of a healthcare example. The billing amount. Well, bill amount is going to usually be a decimal 10.2. A $100 charge must say exactly 100.00, not 99.999 due to floating point errors. Healthcare is full of text, names, addresses, clinical notes. Char of n is fixed length, right padded with spaces, so used when the length is always the same. For example, the state is often a char of 2 for SC or CA for California, NY for New York. Varchar of n is a variable length with a maximum size, and this is the most common text type we will employ. Like first name, varchar 50 stores Joe efficiently without padding. Text is unlimited length, used for chief complaint or clinical notes or discharge summaries. There's no performance penalty versus varchar in Postgres. A best practice, default to varchar of n for most text fields. The limit serves as documentation and prevents data entry errors. Use text without specifying the number of characters only when you genuinely cannot predict the length, like a long clinical narrative. Common mistakes: don't use char 100 for names, like John, because it's going to become John followed by 96 spaces. This wastes a lot of space. You want it to be a varchar, not a char of 100, but a varchar. Healthcare lives and dies by timestamps. Like date, as a data type, is just the date, like 24/03/15. And use this for like date of birth or diagnosis date. You don't need a time component in most of your date fields. Time is just the time, like 14:30:00. Rarely used alone in healthcare. You usually need the date too, so timestamp is date plus time. And you use this for the encounter date and medication administered at. So timestamp Z is an extra wrinkle on this where time zone awareness is incorporated. And this is critical for multi-facility systems spanning multiple time zones. Medication given at 3 p.m. in New York is different from 3 p.m. in Los Angeles. Interval is duration, like 3 days or 2 hours. This is useful for lengths of stay or time to treatment. Critical considerations for any system spanning multiple time zones or regions use timestamp Z, Z for the zone. A patient transferred from the East Coast to the West Coast shouldn't have timeline confusions. The real-world impact: medication timing errors have caused patient deaths. Get your timestamps right. Boolean and special types. These handle specific use cases elegantly. Boolean can be true, false, or null. Perfect for is active, or is chronic, or has allergy. You don't use char of 1 for these fields because someone can put in y or n or 1 or 0. It's too much variability. Boolean is clearer and much more efficient. Then UUID is a universally unique identifier. It's a 128-bit identifier that's globally unique. This is essential for FHIR applications, resource IDs. No central coordination is needed. JSON and JSON binary store JSON documents, and JSON binary stores them in their binary format, indexable, and faster for queries. JSONB is almost always preferred over plain JSON. A JSON binary use case: you can store a complete FHIR patient resource in a JSONB column. You can query individual elements like patient data dash greater than birth date is great for flexibility when a schema is evolving. But you must be careful. JSON binary is powerful, but don't overuse it. If you're always querying the same fields, those should probably be proper columns with appropriate types and indexes. All right, data type examples. Here's how we apply these types to the patient table. The patient ID is a serial primary key, is an auto-incrementing integer. Postgres handles the sequence. Every patient is assigned a unique ID automatically. First name varchar 50, not null, is a variable text with a maximum of 50 characters. Not null because every patient needs a name. Date of birth, date, is just the date, no time. You don't need to know someone was born at 3:42 p.m. Email, varchar of 100 with up to 100 characters, accommodates most email addresses. Could be null if the patient doesn't have an email. Insurance type, varchar of 20 with constrained length, suggests limited options like Medicare, Medicaid, commercial. And created at timestamp, default to now, automatically captures when the record was created for an audit trail. What's the design principle? Each type choice should have a reason. Can you justify every decision to an auditor? All right, let's look at some more examples. Let's look at our encounters table. Encounter ID is a serial primary key, follows the same patterns as patients in the previous example. Timestamp not null means we need both date and time. When did the visit start? Blood pressure. Systolic, small integer works because the range is 0 to 300. It's plenty. Small int saves space across millions of encounter records. Blood pressure diastolic, similarly, small int works. Temperature, decimal 4,1 allows 99.9, 100.4, 98.6. 1 decimal place is clinically sufficient. Weight, decimal 5,1 allows up to 9999.9 pounds or kilograms. 1 decimal place. BMI, decimal 4,1 for body mass index, typically in the range of like 15 to 50. A design question you might consider: why small int for vitals instead of integer? Because it saves space. If you have millions and millions of records, that can be significant. When in doubt, consult this guide right here. For auto-incrementing IDs, use serial or big serial. Let Postgres manage the uniqueness. For external identifiers, like medical record number or FHIR IDs, use UUID, globally unique without coordination. For short text like names and codes, use varchar of n and set reasonable limits. For long text like notes and narratives, just use text with no practical limit. For money, use decimal of precision and like P and S. Never use float. Financial accuracy is non-negotiable. For dates without time, just use date. It's simple. No time zone confusion. For timestamps, use timestamp or timestamp Z with the time zone incorporated. For yes/no flags, use Boolean, not char1, not integer. For flexible or nested data, use JSON-B, good for file resources or schema-dependent data. All right, let's look at our first statement. Create table, the basic syntax of how to bring our designs to life. The basic structure is create table. Then you give it the table name, followed by the column definitions in parentheses. Each column needs a name, a data type, and optional constraints. Table level constraints come after all column definitions. So the semicolon that you see there ends the statement. Don't forget it. You cannot execute a statement without a semicolon at the end. It thinks you still got more to type. So the best practice, you write your create table statements in an SQL file, not directly in the command line. Then you can version control your schema. Every table needs a primary key. No exceptions. The purpose is to uniquely identify each row, like Social Security number for your data. Automatic enforcement means primary keys are automatically not null, and they are unique. Postgres enforces this. There are two syntax approaches. Column level is patient ID serial, primary key, and that's a compact way to say this, and common for single column keys. Table level is primary key, patient ID, required for composite keys and is more explicit. So there's two ways to skin the cat. Let's think about healthcare consideration. You want to use serial or big serial for internal IDs, which are surrogate keys. Store the medical record number and Social Security number or other external keys in separate indexed columns. Why? Because external IDs can change or have duplicates in some source systems. Let's look at a real-world example. A patient has medical record number 12345 at hospital A and medical record number 67890 at hospital B. Your patient ID is the single source of truth. The medical record numbers are just attributes. Foreign keys are how relational databases maintain data integrity across multiple tables. The purpose is to ensure reference values actually exist in the parent table. The syntax is column name, integer, references, parent table name, in parentheses, parent column, close parentheses, and that's the statement. What it prevents is orphaned records. You can't create an encounter for a patient ID 999 if that patient doesn't exist. In the encounters table, patient ID, integer, references, patient ID, and provider ID, integer, references, provider ID, ensures the referential integrity. How is this important in healthcare? Every encounter must link to a real patient. Every prescription must link to a real provider. Every diagnosis must link to a real encounter. So what happens on violation? Postgres races an error and rejects the insert or update. The database system protects you from bad data. Constraints are the rules the database enforces automatically. Not null means the column must have a value. First name varchar 50, not null, means you can't create a patient row without a name. Unique means no duplicate values allowed. Like email varchar of 100, unique means two patients can't share an email. Default autofills if no value is provided. Is active, Boolean default to true, means new records start as active. Check is a custom validation rule. Check age greater than 0 means No negative ages are allowed in your database in that column. You can layer constraints. Email varchar of 100, not null, unique means it must have a value and it also must be unique. So what's our philosophy? You want to push as much as you can the validation to the database level whenever that's possible. Trying to write application code that will verify that fields are within your constraints are easy to program incorrectly and have bugs. Database constraints are enforced consistently, universally, without question. Check constraints let you encode business rules directly into the schema of your data. Like, let's look at gender. Gender validation with gender character 1 check, gender in either M, F, O, or U allows the user to only enter the M, F, O, or U rather than other text fields or an X or 1 or try to put in MALE. Using the check option allows you to specifically limit what entries are legal. Like blood pressure. Blood pressure ranges validation with BP systolic, small integer, check, BP systolic between 60 and 250. So by putting that code in your table definition, every time somebody enters data as the system is operating, it will verify that it meets those criteria. A systolic blood pressure 50 or minus 10 is clearly illegal. Let's look at insurance type. With insurance type varchar 20 check, insurance type in, and then you have a series of text strings. This will verify that the user's entering your internal codes for what are legitimate insurance providers. So this enforces a controlled vocabulary and avoids spelling mistakes like Medicare or Medicaid. You want to be sure that you constrain this at the database design level rather than trying to have code that looks at the text at the time they're typing and has the opportunity to make errors and mistakes. You don't want to corrupt your data. These constraints catch errors at the insert time, not months later when you're running a report and find out there's a bunch of misspelled data in your system. All right, let's look at create table patients. This is a production-ready patients table definition. Patient ID is serial, which means the system is going to automatically assign sequential numbers. It's the primary key. It's auto-incrementing. It's a unique identifier. First name and last name being varchars. Not null means names are required. You can't have a blank name field. Date of birth, not null, is critical for patient identification and age calculations. Gender, carv1 check, uses that control vocabulary we talked about. Address fields are all varchar with appropriate lengths, and nullable if the patient doesn't have an address. Phone and email are contact information and nullable. Insurance type and insurance ID are billing essentials. Primary care provider ID, integer, would be a foreign key to the providers table. Created at timestamp default to now is an automatic audit timestamp for when the record is created. Notice what's not null versus nullable. Names and date of birth are essential. Addresses and email are optional. The encounters table demonstrates referential integrity. Encounter ID serial primary key is the unique encounter identifier. Patient ID integer, not null, references. Patient's patient ID must link to an existing patient. Provider ID integer, not null, references providers and must link to the existing provider. Timestamp, not null, records when the encounter occurred. Encounter type covers office visit, emergency, telehealth, others. Chief complaint text allows why the patient is here today in free text as long as they want. Vital signs all use the appropriate numeric types. Type status, varchar 20 defaults to scheduled, is workflow state with sensible defaults. So referential integrity in action. You cannot insert an encounter for a non-existent patient. The database rejects it. Follow these conventions for maintainable schemas. Use lowercase with underscores for naming conventions. This is a very good principle. It's not mandatory, but it's good coding practice. So, for naming conventions, which is snake case, patient ID, not capital P-A-T-I-N-T, capital ID, or patient, capital I, small d. Postgres, lowercases, unquoted identifiers, anyway. And always define primary key. Every table, no exceptions. You must have a primary key, even junction tables. Don't just document relationships, enforce them. Let the database reject bad data. Add not null judiciously where business rules require values. But don't over-constrain. Nullable has valid uses. Consider defaults. Default now for timestamps. Default true for is active flags. This reduces application code entry. Document constraints with comments in your SQL files, explaining why constraints exist. In the future, you will thank yourself for documenting extensively. Now, alter table, a new command. An overview. Why is this important? Because requirements change. Laws and regulations are always being updated. Alter table is how we adapt to a changing environment. And the purpose is to modify the existing table structure without dropping and recreating the whole table. Why not just recreate? Because of so much existing data, especially with foreign keys in other tables, and relationships and application interdependencies. Common operations include adding new columns for new data requirements, like emergency contact or preferred language or religious affiliation. Dropping existing columns we can do to remove deprecated or unused fields. Renaming columns to clarify names without breaking external queries. Sometimes we change data types to expand capacity, like varchar 20 up to varchar 50, and adding or removing constraints to tighten or loosen rules. Here's a real-world example. A new CMS regulation requires capturing patients' preferred language. So, alter table comes to our rescue. Adding columns is low risk and done quite frequently. The syntax is alter table, specify the table name, add column, specify the column name, and then your data type constraints. A good healthcare example is alter table patients, add column, emergency contact name, varchar 100, followed by alter table patients, add column, emergency contact phone, varchar 15. And when might we see this happen? New regulatory requirements to capture emergency contact information for all patients. So what happens? The new column is added, inserting null values for all your existing records, rows. You can add not, if you try to add not null, you have to provide a default or some value, or else the statement will fail. Existing queries continue to work. They just don't see the new column unless it's updated. So what's the best practice? Add columns as nullable when you first enter them. Then try to backfill the data as quickly as you can. Then you can update the data and say not null once you're sure you've been able to capture the data for all your existing records. You can add that constraint if it's necessary. Another statement type is drop column. This permanently deletes data. There is no undo. The basic syntax is to alter table and give the table name, drop column, then give the column name. And the safer version is to alter table name, drop column if exists, column name, so you don't crash the system if for some reason you misspelled something. Now remember, this permanently deletes all the data in that column on all your rows, all your records. It cannot be rolled back because DDL statements auto-commit. They imply a commit instantaneously. So it may break applications and reports that reference this column. Let's think about the healthcare environment. Do audit requirements require retaining this data? Some laws and regulations mean you have to keep data for years. So archive it first is better policy. Export the column data before you drop it, and then if someone needs to get to that data in the future, they can go to the archived, saved version of that file to retrieve the data that has to be reproduced for legal reasons. So the safest approach is to identify all your codes and queries using this column, archive the data, update the dependent code, and drop it in development and test it thoroughly before you implement it. These modifications are relatively safe but require care, the rename and alter commands. To rename a column, you just say alter table and the name of the table. Rename column like phone to phone primary. And this, you can imagine when this will be used is when we're going to add a secondary phone column. We need to specify the existing phone column to something that's more specific. All right, to change data type, alter table patients, alter column address zip, type varchar 15. The use case, we used to support the zip +4 format, but it requires more than 10 characters, so we change the data type with varchar 15. To add a constraint, you can alter the table patients, alter column, let's say email, and you can set it to not null. The use case where you might see this happen is for some legal requirements, you have to have an email address, like if the patient wants to access the patient portal. So in the table that has that data, the email address field needs to be specified as not null, so that the patient has an active email address to log on to the patient portal. Now remember, type changes can fail if the existing data doesn't fit. Think about this. If you change a varchar of 100 to varchar 50, it's going to fail if any of the records have more than 50 characters. So you have to check your data before you try to execute that command. Here's some real world situations that you might encounter. To add preferred language, for meaningful use, use add column, preferred language, varchar 20. To support zip +4, use alter column address zip type to varchar 15. To make email required for the patient portal, use alter column email set not null. To add ethnicity for demographics reporting, use add column ethnicity varchar 30. To clarify column name, use rename column BP_SYS to blood pressure systolic. The pattern, most alter operations come from regulatory changes, or feature additions, or data quality improvements. So a professional tip, maintain a migration log. Document when each alter was made and why. Very important for long-term management of your data. Invaluable for audits and troubleshooting. All right, here's the granddaddy. This is the dangerous one. Drop table. Removes your entire table, all the rows, all the data. It's gone forever. Your basic drop is just drop table and list the table name. This fails with an error if the table doesn't exist. Safe drop is drop table if exists and then put the table name. But no error if the table doesn't exist, which is useful in some scripts. Drop with dependencies is a drop table name cascade. This drops the table and everything that depends on that table. And boy, is that a complicated mess. Any table that depends on it for its foreign keys and views. Drop only if safe is drop table and table name with restrict. This fails if any dependencies still exist, and is a good test to be sure that if you are intentionally trying to destroy data, that you've eliminated the interdependencies before you drop the table. So key point, unlike data manipulation language, drop table cannot be rolled back. Once it's executed, the table is gone. So you need to understand the difference between cascade versus restrict. This can save your job. Restrict is the default. It fails if any dependent objects exist, which is good. Dependent objects include foreign keys pointing to other tables, or views built on this table, and triggers. If you use it in production, it forces you to understand the potential impact. Now, Cascade drops the table and automatically drops all the dependent objects. So you're going to be deleting records in other tables. Views are dropped and foreign key constraints are removed. You might use this in development and cleanup. It's convenient, but it's very dangerous in production. Like a real example of a horror story, a database administrator ran a drop table patients cascade thinking it would just clean up a test table, but it cascaded to drop foreign keys in real encounters, diagnosis, and medications, corrupted the whole database. So the rule, never use Cascade in production unless you're explicitly mapped every dependency and know there are none that are going to eliminate real live data. All right, drop table. 7 rules that can save you from disaster. First, before you're going to do a drop table, back it up. Have a backup copy so that you can restore it in case you made an error in your coding. Second, clone the production database to development mode first. Third, use if exists when you try to execute the statement to be sure that you have the right table name. And fourth, avoid cascade if you can. Default to restrict, and that way if there are any interdependencies, it will fail. And fifth, by using foreign keys check the foreign keys by running select star from and the information schema table where the table name equals your table, whatever table you're using. And sixth, consider HIPAA. Patient data may need to be archived per retention requirements before it's deleted. And lastly, seventh, document the change. Keep an audit trail. Who dropped what, when, why. The audit trail is essential in healthcare information technology. All right, we're coming to the end for part A. Let's consolidate today's learning. What have we learned? Postgres is a healthcare-ready, open source, ACID compliant, extensible, and enterprise proven database system. It's a great one for y'all to learn, and it's easy enough to learn in just a few weeks. We'll have you writing code in the next couple weeks. Data definition language defines the structure using create, alter, and drop to modify the database skeleton. Data types matter because the right type equals storage efficiency and validation plus performance. Create table with constraints builds quality in from the start. Alter table handles evolution because schemas change, so you want to do it safely. Drop table requires caution because it's irreversible. Always back up first. Constraints enforce integrity by pushing validation to the database level, not to your code. After this session, practice by writing a couple of create table commands for a small project. Muscle memory matters. Experience is a good thing. And that's it for this part. And a little bit later, we'll come up with part 4B, the data query language. So we talked about creating the tables, the data definition language. Now we're going to move on to the data query language, where we do the select, where, and order by. And that's the nitty-gritty of your programming. So once we've created the table in the data definition language, then we'll be using data query languages to find records that we want specifically for reporting or updating. So the where, the select statement is the fundamental query building block. Where is a clause that filters the rows based on specific conditions or comparison operators like equals or not equals, less than, greater than, or between, or like in a list. And order by allows us to sort the results so that you can print reports meaningfully and do practical exercises. And so we'll be doing some real exercises and examples, and you'll have some fun in playing with some data in tables and see how easy it is and how powerful the system is to allow you to create real life examples and things that are going to help you become a more productive and valuable member of your team. So currently we built the container, and next time we'll learn how to find out what's inside. Look forward to seeing you then.